And I'm delighted to be here to talk about, following up on the talks you heard yesterday, talking about high harmonic generation, which is the complementary process to the strong field ionization talks we heard about. And in particular, I'd like to talk about some new developments. One of them we call the ultraviolet surprise, that it turns out that just going back in history to almost 30 years ago, harmonics were first observed using ultraviolet lasers, and it turns out that we're now using ultraviolet lasers again, and I'll explain why we're doing that. And then the other topic I'd like to talk about is that we now know how to make bright circularly polarized high harmonic beams, which we did not expect to be able to do, although the theorists had figured this out way back at the beginning of high harmonic generation, that you could make circularly polarized harmonics from a single atom. And what we then figured out how to do is how the phase matching physics work, and can you actually make that bright? It turns out it's also very favorable. So just some interesting new developments, and from the point of view of young people in the field, it's very nice that we still don't know everything. So there's lots more work to do. I don't do this work alone. A lot of collaborators from all over the world. Some are, and I'll mention their names as I talk about our joint work. And so, just from a 40,000 foot perspective, what is surprising to me, I started out in plasma physics, making X-rays from laser-produced plasmas, which is essentially trying to make an X-ray light bulb. Heat a filament, except with the laser you can heat it to the temperature well beyond the temperature of the surface of the sun, and it emits X-rays. But in plasma physics, we have absolutely no control over those X-rays. They're unstable. They emit into 4 pi. You can't get a short pulse. All of the challenges of trying to control plasmas, and that's why from as a sort of an older person in the field, I am still amazed at high harmonic generation, because the X-ray fields we produce are better behaved than the laser fields we use to make them. And that just seems strange. Paul knows this because, of course, he did lots of work in laser plasmas when we couldn't really control that short wavelength light. And this is why I am still, even though high harmonics have been around now since the late 80s, they're still just remarkable, because think about it. So in the visible region of the spectrum, we can make these beautiful cones that span an octave. Well, with high harmonics, we can have a cone that is synchronized to less than an attosecond, but it now spans 12 octaves in bandwidth. The temporal coherence is, sub-attosecond. You can't, and I'll explain why you couldn't even see a beam if the X-rays were not synchronized to less than an attosecond over macroscopic physical dimensions. And to me, that's sort of amazing. The spatial coherence is perfect. Now we can make linear and circularly polarized harmonics, and we've even figured out how to start to measure them. And so to a great extent, again, coming from a plasma physics perspective, we had really no expectation that this would be possible. It just, and so we have wonderful control over X-ray light using visible light. And sort of following up on what Linda said yesterday, she talked about how difficult X-ray optics are. They're expensive. You have to polish that optic to a fraction of the wavelength of the light, and there's no lenses, good lenses. But fortunately, through the beauty of quantum mechanics, we can actually, instead of using an optic, we can start to, it's a different version of quantum optics, but that we can sort of play with the laser beam direction, and I'll tell you how this works, to then separate the harmonics each harmonic comes out in a different direction, so that's kind of like a quantum grading. Because we can play these two color fields, and I'll explain how those works. We essentially have a quantum waveplate. Because we can change the color of the driving laser and then change whether the emission emerges as a single burst or as multiple bursts. We essentially have a quantum Pockle cell. And because we can also, we haven't done this yet, but because we can play with the quantum phase of the electron by adjusting the light, the laser field that's present, in theory we can also make a quantum lens. And so it's really beautiful that we can sort of control the X-ray light by using the laser light to control the quantum wave function of the electron. And so the precision of this light source is now being making it possible to be used. And in our lab, we really are trying to look at what can we see and learn about new materials and nanoscience. And I'll talk about some of these applications in the next two lectures. So maybe enough said there for now. And for the young people in the audience, I just wanted, to point out that, and again, from a historical perspective, we've had coherent beams in the visible region of the spectrum for over 50 years now, just about 55 years. And of course, when the laser, when it was first demonstrated, was called, a solution looking for a problem. But of course, we now know the laser powers the internet, used in medicine, of course, science, of course, but also ranging, surgery, optical storage, and such. But in that 55 years, you may not know, but the shortest wavelength laser that's in widespread use is the excimer laser at 193 nanometers. And so when you take that ratio of the first ruby laser that Neyman demonstrated and the excimer laser, that wavelength shift is less than a factor of 4. And when you think about most areas of physics, if you talk about electronics or Moore's law we were talking about, all of those have changed by like 11 orders of magnitude in terms of our capability. But in terms of lasers in widespread use, that wavelength has changed by less than a factor of 4. And what we're excited about is that harmonics have a possibility of actually being a light source that cannot address every application, but for some applications they can, in photo emission and imaging and others, that they certainly can be a light source that's accessible in widespread use. And as Linda said, they are very complementary to the large-scale facilities. If you look at their relative merits, and here I just showed a picture of the advanced light source, a synchrotron light source, but of course we can also compare with the beautiful free electron lasers, and then see, so just again a very quick comparison. Of course, the facility scale sources can go to much higher photon energies for now. We can, with harmonics, we can go to a keV, but there is no physical limit to it in the physics that we understand. That doesn't mean we will be able to get to hard X-rays, but we don't see any physical limit yet. So there's a possibility we can get to higher photon energies. The synchrotron sources have nanosecond time resolution, and of course with the free electron lasers that went into the femtosecond range, but with the harmonics we're already, as you know, well below femtosecond. If you think about, one of the big uses of X-rays are in microscopes. So the best microscope, as we might think about it, where you take a material sample and stick it into the microscope and take an image of that material. So the best X-ray microscope that anybody can make is shown here. It's work done at the Advanced Light Source, and it's a 5 nanometer spatial resolution full field image. And we can get to about 20 nanometer spatial resolution with harmonics, and there's no reason whatsoever that that's not going to go to the same physical limit as the synchrotrons. Of course, the wonderful thing about the facility scale sources are very high fluxes, so you can do single nanoparticle imaging, for example. They're tunable, but high cost and limited access, which is an issue. For example, the National Renewable Energy Lab is just down the road from us in Golden, and when they make a new photovoltaic, they can get synchrotron time every 6 months, and in between, if their sample changes, they don't know if it's X-ray damage or if they just made it wrong. So any kind of iterative design needs frequent access to some characterization tools, and that's where harmonics can really be a solution, because for the applications it can reach, you can have it in your lab and really iterate a lot of nanoscale properties. So we have medium flux, but we are what we call hyperspectral. I'll talk about that in my imaging talk. The fact that you've got multiple colors, now we know we can shine those colors on a material and do spectroscopy or imaging all at once, and that gives you very nice chemical contrast, and tabletop and low cost. So I think after yesterday's talk, I hardly need to show this. We know in a strong laser field, and AMO can undergo tunnel ionization, and you get this beautiful sequence of harmonics with a plateau and a cutoff, and that maximum cutoff is just given by the ponderomotive or regular energy of the electron in the laser field, and that just scales with the laser intensity and wavelength squared. So if we want to get high order harmonics, you will either have to increase the wavelength or increase the intensity. And for quite a while we thought that only increasing the laser wavelength made sense, but now we understand actually increasing the intensity also works, but only in the ultraviolet. Okay, so what's shown here are some quantum movies that Carlos Hernandez Garcia made for us, and it just shows the wave function of the electron in a linear and that is ionizing, undergoing strong field ionization in a linear or a circular driving laser field. So in the case of the linear driving lasers, as the atom undergoes tunnel ionization, the electron wave packet is driven back, you get these beautiful quantum interferences, and it is those quantum interferences that makes it look like you're wriggling that electron at much higher frequencies. And that is the quantum origin of these harmonics. But we've known for a long time that if you irradiate the atom with a circularly polarized laser, sure enough, it undergoes strong field ionization, but because the laser has circular polarization, the electron never goes back. You don't get any modulations on the wave functions, no recollision, no X-rays. But what has been known for almost as long as the linear polarized case is the fact that if you took two color lasers, both circular polarization, and irradiate an atom with that field, you get the best of both worlds. The atom undergoes strong field ionization. Did I hit something here? Undergoes strong field ionization, but can also recollide. And I'll explain how that works. And because you're driving with circular polarized field, but you're enabling a recollision, then you have to get out circular polarized X-rays. So this is the beautiful single atom strong field quantum physics. It's really, really beautiful. And what our group will spend our time doing is how do we take that single atom physics and try to make a bright beam that we could use for applications. The emission from each atom is a dipole emission. It's a dipole transition from the continuum back to the ground state in most cases. And so that emission, of course, has the normal dipole emission, spatial distribution. And if you want a beam, what you have to do is take the emission from many atoms and have them interfere constructively. And so essentially what that means is that if your laser comes and generates a harmonic from one atom, then you have to set things up so that both the driving laser and the generated harmonic both travel at the same speed in the medium. If that happens, then the harmonics generated in different positions in the medium will interfere constructively. You'll get your quadratic increase in signal, and you'll get a beam if you do that with enough atoms. And you might think, well, how hard could that be? But think about it, no matter deflects X-rays. So that's essentially saying they're not bent by materials. So essentially that means that the X-rays are always traveling at the speed of light in the material, or a refractive index of 1. But we know that in any neutral gas, for example, visible light will it speed up or slow down? Anyone has to guess? It's like glass. So light, does it speed up or slow down in glass? Slows down, exactly. So this would not happen in a neutral gas. Now, does anybody knows plasma physics, what happens to visible light in a plasma? What happens to the phase velocity of visible light in a plasma? Does it speed up or slow down? Yeah, for the old plasma physicists, we always remember that in a plasma, the product of the phase velocity times the group velocity is c squared. The phase velocity speeds up faster than c, but the group velocity slows down. So there's no violation of anybody. Nobody is upset about that. So essentially, you're trying to do this phase matching in a medium that's sort of schizophrenic because it starts out as a neutral gas. It becomes a plasma. So the laser is always going either too slow or too fast. And so for a long time, back in the early 90s, we didn't even think you could do this under any circumstances. But fortunately, as and this does not change as you get older, nature is always smarter than we are. So this is what saves us. Right. And so Carlos made this little illustration of how hard it is, because particularly when you're using long driving laser wavelengths and the single atom yield is low, what you're trying to do is use your laser as a quantum conductor that's sort of orchestrating the emission from the same number of atoms as there are people on the planet, and they all have to sing in tune at the same time. And the disparate wavelengths make it surprising it works, because we're driving with maybe tight sapphire or some mid-infrared light, so wavelengths from 800 to 4,000 nanometers, but we're making X-rays with wavelengths of between 1 and 30 nanometers. And if your wavelength is 1 nanometer or 10 angstroms, you have to synchronize to a fraction of that if you're going to add all these waves in phase. And so the fields have to add with sub-angstrom spatial resolution and sub-attosecond temporal resolution, because at a KeV, a single cycle is 2.5 attoseconds. And so you have to get the synchronization to much less than a single cycle, or everything interferes destructively. So it's amazing it works, and it only works because nature is willing to do it. I'll show why, because we would have no hope of doing this with electronics. There's just nothing anywhere near this precision. So the only way we have it as physicists is to sort of figure out, what's the physics and make the physics work for us. And so that's what's illustrated just in this single view graph. So on this light and dark color lasers, what it shows is the laser field at the entrance and at the exit of a medium. And then what's shown in green is the ionization that happens as the laser field increases. So this is the leading edge of the laser pulse, and as, of course, the ionization happens near the peak of the field. Now, some electrons go back. That's why the ionization dips. This is the quantum calculation, and it's lumpy because some are pulled out, never to return, depending on when they emerge, but some go back. So the ionization goes in this little lumpy series of steps. And this sort of illustrates the problem with phase matching, that the leading edge of the laser is traveling less than c. The trailing edge, when there's a lot of plasma, is the trailing edge of the laser is traveling at a phase velocity greater than the speed of light. But fortunately, there is a cycle where you see the two fields at the beginning and the end of the medium overlap perfectly. And so during that single cycle, as it travels through the medium, any X-rays that are generated in that cycle interfere constructively. So some of the laser can phase match, some of that. And it turns out that width of that phase matching window depends on the color of the driving laser. And it can all be calculated on this very simple formula that really is not even time dependent, but you can only use that formula if you only apply it to the part of the laser beam that is traveling at the speed of light in vacuum. And so during that little window, sure enough, the X-rays will naturally, if you set up your geometry right, and you can get a coherent illusion of the X-rays generated in this window.
I have a quick question.
Sure.
So does that make it less susceptible to pulseration because you have this sweet spot, or?
It does, fortunately. It's somewhat scheme dependent, but in many cases it is much less sensitive to things like phase fluctuations and other things than you would not normally think about in a highly nonlinear process like this. And so if you take that and plot the predictions of where should you be able to phase match up and up to, what's plotted on this little plot is the color of the driving laser wavelength from the ultraviolet through high sapphire that many of us use into the mid-infrared region of the spectrum. And the solid lines, what they show are the predicted phase matching limits based on a sort of more slightly, but not a whole lot more sophisticated version of this formula. And then the dots are where we confirmed these predictions experimentally. So it looks, pretty good, actually, amazing for a very simple, non-analytic, quantum approach. But we've also verified that if you put in a full quantum calculation and do the propagation, you actually also get the same results. We don't do it, but our collaborators in Salamanca have done that. And so, for example, and I just wanted to point out, just again back to the phase matching physics, so why does this work? Why, as you go to the mid-infrared region, can you get phase matching up to the soft X-ray region of the spectrum? Fundamentally, it's sort of just back to the Ponder mode of energy. The oscillation energy is just given by the I lambda squared. If you turn up the wavelength, you need less intensity. What will happen to the ionization in the medium if you have a lower intensity? Does it go up or down? If you hit the atom less strongly, will it ionize more or less? Less. Thank you. And so if you've got less ionization, you don't have to work as hard to pull that laser, to stop that laser going faster than the speed of light. The phase velocity. Sure. Sure.
On the previous slide,
Sure.
what's the longest wavelength you were able to?
That we've tried, the longest wavelength we've tried, we did this with Andrus Baltuska, and it's a 4 micron laser, because he had all these other wavelengths we had in our lab, but he has these very high energy. We spent a long time trying to understand phase matching. He had spent a long time building mid-infrared lasers for all kinds of science, and so he had this nice 4 micron laser that we could use to validate this. But there's a lot of other people building mid-infrared lasers now. It'll be great to test because we actually, it's very hard to do the calculations, as you know better than I do, Tony, that because as you go to longer wavelengths, your light cycle is getting longer, but your X-ray cycle is getting shorter. So even the calculations for a tiny propagation distance are really hard, and just computationally very challenging. So, we're hoping that people will come up with the right theoretical approximations so that there can be some theoretic predictions, because we'd love to know what is the longest laser wavelength that's worth trying to produce. But you still need to ionize.
The criterion for choosing is?
Well, it has to ionize, so it has to be able to ionize. It has to be, tunnel ionization, am I right? Because only with tunnel ionization do you get the perfect synchronization. Because if those electrons, when they're born, are not perfectly synchronized, you lose the
Just a question.
Sure.
When you say theory tell you whether it's worth pursuing higher,
yes.
what theory are you looking to
Okay.
give you?
So for example, we're wondering. So already at 4 microns, we were surprised actually that it was that simple, because what we thought is with 4 microns, if you calculate, those quantum blobs we had the movies of, if you calculate the extent to which that wave function spreads, it's already comparable to the spacing between the atoms we use 80 atmosphere gas pressure to compensate for the low single atom yield. We didn't know if there was going to be some scattering from adjacent atoms. Fortunately, the ionization is low, so it probably doesn't encounter an adjacent ion. So that helps. But then as you have 3D quantum diffusion, and you're trying to coherently add those waves, and the wavelength is getting shorter, at some point, it would be interesting to ask, so when does that perfect synchronization start to vanish? When does scattering from adjacent ions start to give you some decoherence? So there's many sources of decoherence, just on all the same physics that we used with shorter wavelength driving lasers, but now with much more spread out quantum wave functions and shorter wavelengths. At some point, the quantum coherence of those waves may or may not be as perfect as they are now. So essentially, just summarizing what our understanding was until about 3 years ago, we had that if you use Tice sapphire, you could make light up to about 150 eV in the extreme ultraviolet region of the spectrum. If you used a 1.3 micron, you could get just about to the carbon edge. If you used a 2 micron laser, you could get to the oxygen edge. And if you use this 4 micron laser in very high pressure to compensate for the low single atom yield, you could get essentially a white light coherent continuum that sort of goes all the way up to the KV region of the spectrum. We had all of these lasers, but we didn't have that laser, and so collaborating with Andrus Baltuska was very important. And this is Ming-Chan Chen and Tanya Potnichev, from our group, this was their thesis work. And this is the only way to make a coherent X-ray beam on a tabletop. These highest orders that you see here, at 4 micron, each photon is 0.3 of an EV, and if you divide 0.3 into 1500, you get 5,000 orders, and it's still a perfect beam. As I said, it spans 12 octaves, and of course spans many absorption edges, but the whole physics of the process means that we would not see a beam which we do, we see this very nice beam at 1 nanometer, and you would not get such a nice beam if... Okay, so we wanted to just confirm that we understood everything and fill in the experimental validation at shorter wavelengths. And so this was the predictions, and this was our initial measurements. But then we have slightly more intense lasers in the short wavelength region of the spectrum, and so we started to turn up the intensity, and then we got this surprise, which we're calling the ultraviolet surprise, which is different from the usual one. We suddenly saw harmonics that were as bright as if you used the long wavelength driving lasers, but they came out as discrete peaks, like they normally come. And, you know, we all know how to do Fourier transforms, all right? So if your harmonics come out as a single burst, what in time, so an isolated burst in time, what kind of spectrum must that correspond to? Yeah, what kind of Gaussian? Yeah, it's a continuum, all right? Because to be able to make an isolated burst, you need a fairly broad continuum. And that's what this does. So this phase matching window, and we've confirmed this experimentally for long driving laser wavelengths, the phase matching window is less than half an optical cycle. But you look at this, and you can immediately say without any, you don't even need to do any quantum calculations or anything, but if you've got a periodic spectrum, got a cone, then your phase matching window doesn't span one cycle or multiple cycles. Yeah, it has to. This is just Fourier transform. We don't need to use any physics. So this had us scratching our heads. What is going on? How can phase matching suddenly occur over multiple cycles? We understood things, like I explained, that on the leading edge of the pulse, the laser was going too slow. On the trailing edge, the laser was going too fast. But suddenly, how does the laser seem to go at the right speed for multiple cycles of the driving laser? And of course, we scratched our head, we looked back. I mean, why wasn't this seen before? Because actually, the first harmonics were done, because the first femtosecond lasers were often, the first powerful femtosecond lasers were based on exomers. Those could pack they had a lot of energy. So we went back to see, well, why are we seeing this and why wasn't it seen before? And in fact, there's some beautiful work that showed that if you used a 248 nanometer krypton fluoride exomer laser, they had a lot of energy, maybe 100 navijoules or something. They had 400 femtosecond pulses, and you could see they saw harmonics down to 5 nanometers. But they were very low efficiency, 10 to the minus 12. So not phase matched. But we were seeing them bright as a well phase matched beam. So, in fact, this is the experimental data, and you can see you expect very bright harmonics for ultraviolet lasers in the vacuum ultraviolet region. The cycle time is much shorter if you've got a short wavelength laser driver, so there's less quantum diffusion. So it's this really bright single atom emission, and you expect that. But what we didn't expect was this plateau that went all the way out to 300 eV, and that optimizes at very high pressures, 400 torr. And our colleagues in Salamanca, Luis Plath's group, did this calculation where, because tunnel ionization still, and strong ionization, still applies, and very appropriate for UV driving lasers, and so they calculated what ionization stages must be present for us to be seeing emission from argon. It turned out this was from argon in this region of the spectrum, and these emissions had to be coming from multiply ionized ions. Now, harmonics from ions had been seen before, but what had not been seen before was bright emission from ions, and and so then that got us thinking. So what is different about refractive indices in the ultraviolet region of the spectrum? Do they get bigger or smaller for light as you go from the visible to the ultraviolet? You will learn in undergrad that the refractive index does it go up or down? It goes up, yeah. And it goes up because, of course, you're approaching all the resonances in the ultraviolet. Now, you think...
You don't get sunburn if you're sitting in a car.
Exactly.
That's the glass.
Exactly. So they go up, yes, exactly. And they get, absorbing, yeah. So if the refractive indices goes up for the laser, does that make it easier to slow the laser down or harder? I know I'm asking a lot, first lecture in the morning. So what is the phase velocity of light is given by the speed of light in vacuum divided by the refractive index, all right, C over n. And so if n goes up, the phase velocity would tend to slow down. So it turns out in the ultraviolet, for ultraviolet driving lasers, because the refractive indices of the atoms, and not only atoms but ions, because you can't neglect, in the mid-infrared the refractive index of an ion is very low, but if you calculate the refractive index of an ion in the ultraviolet, it's still quite significant. So you get help in phase matching. So what happens is, as you go from the infrared through the visible through the ultraviolet, the linear refractive indices of atoms and ions increase, but any influence of a plasma decreases. And so it becomes easier to force the laser to travel at the speed of light in vacuum. So phase matching becomes easier. And that has you win in two ways, because your quantum diffusion is less, because your cycle time is less, so the electron spends less time in the continuum. So if you look at the quantum diffusion, there's less transverse quantum diffusion. You have to give it the same energy.
And Margaret?
Yes.
What is the fractional ionization typically?
It's very
high.
So if you drive with high sapphire lasers or with mid-infrared lasers, if you want to phase match, then the fractional ionization is less than 10%, and sometimes less than 1%. But for ultraviolet lasers, you can go up to 4 or 5 times ionized and still phase match. And that is just weird. I mean, because again, coming from a plasma physics perspective, in a 5 times ionized plasma, we would say nothing is possible. But, there's strong plasma gradients everywhere. And so the fact that harmonics will phase match it under these circumstances are actually quite surprising to us. And so what we've plotted here, it's a bit complicated, but it shows this phase matching window in yellow for the normal way one would do harmonic generation for Ti sapphire compared to these UV driving lasers. So you can see for Ti sapphire you get, depending on you can modify the conditions a little bit, but it's a couple of cycles, 2 or 3 cycles. You can make it go up to 10 if you want. But for the ultraviolet driving lasers, the phase matching window is much broader. It spans multiple cycles, which we know it must, because you get these very narrow peaks. So, but it was nice that that actually an analysis could show that. How am I doing? I'm doing okay time-wise, am I? Or
Yeah.
Okay, good. So then, Tony, we don't know the limit in either direction. So it's very interesting what will be the best route. And then what happens as you approach ionization potential. So there's a lot of really interesting physics questions here that would be great to shed some light on.
I'm still a little bit puzzled. As you go to longer driving wavelengths, the phase matching property for the driving laser gets better.
Yes.
But you're producing many higher orders of
Correct. It's a much higher order process. Correct.
And so the index of refraction probably you get.
And delta K, and the phase slip is, delta K is always, K times the fundamental minus the delta K, you know, and so your phase matching in some ways you would expect it not to work because your order is going up so high, and it does because of, again, strong field ionization. It all comes back to because, you know, it's, and the harmonic scaling is I lambda squared. So as the wavelength goes up, your intensity goes down, and in the infrared, tunnel ionization is favored. Right, because your field, you're depressing that barrier for an eon by the time you're when you're at 4 micron driving laser, your cycle is 13 femtoseconds. So you pull that poor atom and kind of held it there, essentially for many femtoseconds. Right? But it's amazing to me that the synchronization is so perfect. You know, there is no any kind of decoherence at all. But I guess it's just because in the infrared, you know, it is always tunnel ionization will always win versus multiphoton. So many physics questions that can be addressed as, you know, we'd love to see some more theory that explores these limits because, you know, things we thought would be an issue like, you know, the Lorentz force. You can take care of those with other applied light fields. So, you know, they're, to our knowledge, and of course this is famous last words as an experimentalist, we don't know where the limit is, but that just is we don't know where the limit is. Yeah. And so then, maybe I'll talk about circularly polarized harmonics and phase matching in those fields. The ideas have been around for quite a long time. Work from Wilhelm Becker's group in Germany and his collaborators. And so, so let's see how we think about it. So, and this is work we did in collaboration with Oren Cohen's group at Technion. And so this is the fields of two counter-rotating circularly polarized drivers. And if you look at, so what do these two light fields combine to? And depending on the relative intensity of these two light fields, you'll always get something that's threefold symmetric for these, for the fundamental and second harmonic of tri-sapphire. And if you do the right ratio, you'll actually get this clover leaf that's not special. In fact, clover leaf is not the one you want, but it's still a threefold symmetric thing that has lobes, 3 lobes like this. And where would the electron ionize in this field? Would it ionize here, or here, or here? Where would the electron tend to ionize? At the peak of the field, right? So it ionizes 3 times the cycle, and then returns, and that's what we were trying to convey here. They come out here, here, and here, and then fraction of a cycle later, the electron returns, and you get the X-ray bursts. And this is how you can think about how you get these circularly polarized photons out. Each harmonic photon has to be the combination of the different circularly polarized photons you're irradiating the atom with, but because it can only take away 1 unit of photon spin angular momentum, you can only grab 1 more red than blue. You can grab 1 more blue than red or 1 more red than blue, but you can't, that is the only combination that's allowed, because otherwise it doesn't conserve photon spin angular momentum. So you have to get out either a right or a left circularly polarized harmonic. And so that's essentially saying this, that to conserve energy, I just add the number of blue and red photons, and to conserve angular momentum, I can only have 1 more or less of the 2 fields. And this has been known for quite a long time. So what was not known is how you think about phase matching. And normally, if you do 2 color linearly polarized laser fields to make harmonics, will red and blue light travel in any medium at the same speed? Do you want to hazard a guess? Yes or no? Do you think?
No.
No, exactly. And the reason why is that there's some phase slip that they propagate. And while you could, and so the intensity will modulate, and you can do a quasi-phase matching based on this, but in general, you won't do perfect phase matching. But think about these circularly polarized fields if there's a phase split between the red and blue, which will happen as those fields are traveling through the medium. All that will happen is your combined field rotates. And now your max intensity is not changing as you're going through the medium, it's just rotating slowly. So phase matching works even though you're using multiple colors. It's still perfect. So you can do as well as linear. So that's how you get the bright beams. I won't bother with the math, but this is fun if you're bored, and it is fun to do these calculations to work out the conservation of energy and photon spin angular momentum. And it's a lot of fun if you use non-commensurate colors. So we did that recently just to see if we could do this in the soft X-ray region. And I'll finish up in a few graphs here. So instead of doing 800 nanometers and the frequency down below 400 nanometers, used 800 nanometers and 1.3 microns, the mid-infrared, which is the same approach you use to make linearly polarized soft X-rays. But now they're non-commensurate, so it takes a little bit of, you can work it all out, and then what you find after much ado, we drove ourselves crazy, all the theorists and experimentalists trying to figure out what the selection was for and what's happening. But essentially, for these pair, you get a beautiful 8 bursts in 13 femtoseconds. This, so our 13 femtoseconds is the common multiple of the two colors, and so 8 times. The electron, of course, just like Lars was talking about yesterday, the electron is born far, born in, away from the ion because it's born at some position where it tunnels, and so it's born here. And then for the right intensity ratio, it will take a trajectory. The ones that give the harmonics are the ones that go almost linear and then return. And they're doing that 8 times per cycle. Not per cycle, 8 times per 13 femtosecond, which is just the repeat time of the fields. And phase matching works there too, because if they're phase locked, you get a 3-fold symmetry driving field that doesn't rotate. If there's a phase slip, it rotates, but doesn't matter. And if they're non-commensurate, it does something strange, but it's still not, essentially it's just rotating. And so phase matching works there too. So you get this, again, the beautiful pairs I already showed you in the EUV, that they go up now to about 150 EV, which is nice because this matters for, there's interesting magnetic materials in this, with edges in this region spectrum, gadolinium, which is very interesting scientifically. And we took a look at this and saw, well, what is this? Why is our circular polarization not perfect? In the EUV, you get these beautiful pairs. The conservation of photon spin angular momentum kills all the harmonics in between, so you get a left circularly polarized harmonic, a right circularly polarized harmonic, and a missing harmonic. Here, because we're using non-commensurate lasers, they're grouped differently. The difference is just the difference in these wavelengths, and the sum is just and here's one is the sum, one is the difference. We were wondering what this continuum was, but we got these hints because these peaks are coming where you don't expect them to be from conservation of photon spin angular momentum. But then what we realized, what they must be due to are imperfect wave plates. Yeah.
Why are you calling these non-commensurate? The
ratio, fine. So that's, yeah, you're right. Yeah, just a slip,
Okay.
a wording slip. Yeah.
Okay.
We went through lots of ways we were talking about
Okay.
So, but then we realized, it's hard to get good optics in the mid-infrared, and all that was happening was that our ellipticity was not quite perfect, and the way our terminology, we started talking about buckets. So we said, well, you got this, because you can only take one more photon from one bucket than the other, and then what happens if you've got an imperfect wave plate, because as you're going into the mid-IR, you've taken more and more photons, and so you could grab a wrong polarized photon. In fact, it's more likely as you go into the mid-IR. But in other words, this is just to show, it explains beautifully a tiny amount of ellipticity in your driving lasers will give you this underlying continuum. For a while, we thought, you see, it was phase matching, and there was some, because you could imagine cases where, especially in your cutoff, your phase matching window will be narrow, and then you don't get 3 bursts, and you might get a continuum, but that's not it.
I have trouble because I'm read colorblind.
Oh.
I just want to understand, these pairs,
Yes.
what distinguishes them? It's not
The
their-
circular polarization.
One is right,
One is
one is
right,
left.
one is left, exactly. And that's just because one corresponds to taking one more red photon than blue photon, and the other one more blue than red. So they're separated by the difference, and also the sum. And the reason this was important was that we don't need perfect optics, because if we know what the ellipticity is, we can work out any magnetic material asymmetry if you know what your ellipticity is. And we can just get gorgeous agreements with more sophisticated models also by just knowing what this shape of the spectrum looks like. It tells you immediately what the ellipticity is, and so you can apply it to any current molecule or material. And we actually did that just to prove to ourselves we kind of that everything was good. We just measured the magneto-optic absorption coefficient of iron, compared it with synchrotron data that's in the EUV, and then of gadolinium that's at 150 eV, and also compared it with synchrotron data. It just shows that we can actually, we understand the polarization state of the light. And I think in perhaps I should finish in 5 minutes, is that okay? To just show you in work with at the School of Mines and Luis class in Salamanca, we extended the beautiful work Paul's group and others did with crossed beams, but now if you use crossed circularly, oppositely polarized circular beams, you then send all of the right circular polarization harmonics in one direction and the left circular polarized harmonics in the other direction, which is kind of cute. And this just shows you the 0 order if you cross. And so if you do it right, you can actually separate them spatially. Each harmonic comes out at a different angle. And you can sort of see that from this, again, just a photon picture. This is your EUV, the left and right circular. If you want to get the next order, you've got to add 4 of these and 3 of these. And so that'll automatically make every harmonic comes out at a different divergence angle. For another, maybe what I wait to one of the later talks this afternoon or tomorrow and talk about how do we measure these light fields, because we are used to the linearly polarized light fields and how to measure them, but with the circularly polarized light fields, the direction of your electric field is changing, and so this is, theory what it should look like for one of these circularly polarized harmonics. This is just the 2 projections, and of course there's a phase difference between the 2 of them. And then the question is, how do you measure this light field? And so maybe with that, I think I'll end just because of the time. Thank you.
Thank you very much, Margaret. Let's see if students come first. Any student before he steals the show? Here in the back.
So you talk about this closed shape,
Yes.
and it rotates, I think.
Yes. Yeah.
And you see the harmonic generator at each of the poles.
Yes.
So you have different polarizations. And do they still phase match?
They do, because remember, for each one of those harmonics has to take one more or less red or blue photon. So the selection rules are still very stringent. So they still phase match. The rotation is very slow, much slower than, so the rotation is slow enough. So
Tony.
that's fortunate.
For your last slide was right and left circularly polarized. I don't think you have to show it.
Okay.
What is the temporal duration of these harmonics that are right? Absolutely.
So you know, essentially for the most part, especially with the cones, when you're looking at the cones, you can sort of back of the envelope even just do Fourier transform, and because they're not very chirped, because they get more chirped as you go to very long driving lengths, but they're not too chirped at all for these colors. So you know immediately you can take a look at this and say these are phase matched over multiple cycles. And so
Are these hundreds of attoseconds, or are they few femtoseconds? I mean,
essentially that's the theory. Yes, a good question. Yes. So let me show you exactly the calculation here. I may not have the perfect one, but this is a good. Yes. So this is for the cross beam case. For the cross beam case, that's not what I want to say. Okay, maybe I. This is the collinear case. So yeah, this is the actual theory prediction, and if we can see the so you can see here. So each burst is 200 seconds. Yeah, which is very much like what linear polarized EUV harmonics when you're not using some kind of gating.
Seconds roughly.
Yes, that's right. And with the collinear case, because you need, trifoil, because if you restrict the phase matching to one cycle by using some polarization gate or other things, then you will get linear, because each burst is linear. And it's just they add together and they phase correctly to get circular. But with the cross beam case, you can actually make an isolated attosecond circuit polarized burst, but not with the collinear. So that's why with the cross beam, with the collinear, you get very nice narrow peaks.
Yeah.
I have a question about the HSG from the different charge states.
Uh-huh.
So the calculations, was that done for each charge state, or like for the system? Like, do you have to include like a volume
Yes.
averaging type?
Exactly.
calculation?
So it was done as sort of analytic. So if we had our theory collaborators calculate what, where the charge states lived, and then built those into a code that with another code from Livermore and Bob Levis to do with Tempo that estimated, it's not quite right, but can estimate the linear and nonlinear contributions of the different ions. So we could do, this is still the theory on this. I mean, we know it's roughly, it's correct. We get the right 10 femtosecond or 30 femtoseconds. I forget what, a 10 femtosecond temporal window, I'm pretty certain, which in the UV is many, many cycles. Because it's, it's 1/3 the Tie-Sapphire cycle. But I would say that the theory is not as refined at all as with for the regular, phase matching partially ionized.
And that was done in a fiber cell?
It was done in fiber cell, and what we see is if there isn't some kind of structure there, there's also nonlinear effects happening. We can sort of see that there's a filamentation process happening also, and not surprising because we have to use a very, very high intensity. Because I lambda squared, if lambda is small, I has to be 10 times higher than Tie-Sapphire for the same energy. So not surprisingly, and because of the multiply ionized plasma, you do see some filamentation, and not surprisingly also, if there's some kind of structure around the beam, it enhances that filamentation. Again, this is not super surprising for those of us who've done filamentation either on purpose or by accident multiple times. But so the geometry matters, but in a different way. You don't need very high pressures because the single atom yield is so high. So we use 400 torr, less than an atmosphere. But we did find it doesn't work quite as well in just a cell or a gas jet. And again, just because we need help from nonlinear, maybe if we had a more powerful laser, that would not be true, but because, you know, a plasma tends to defocus the beam, so that's what we might be getting help by some launching conditions.
Yeah.
I don't think I quite understand